We're going to begin Chapter 6 with Section 6.1 on Antidifferentiation. The primary focus of calculus is on finding the slope of a curve at a point or finding the area of a region under a curve. So far, we've spent primarily the entire semester focused on finding the slope of a curve at a point, aka the derivative. So starting today, we're going to move on to finding the area under a curve, which is what we call antidifferentiation. So when we are given the derivative of a function f prime of x, we must find the function f of x. This process is what we call antidifferentiation, or oftentimes called integration. Let's start with a pretty straightforward example. Example number 1 says find all antiderivatives of the given function. F prime of x equals 9x to the 8th. So what we have to do is we have to figure out what function has a derivative that is 9x to the 8th. While the derivative of x to the 9th is exactly 9x to the 8th. So that means that x to the 9th is the antiderivative of 9x to the 8th. But so is x to the 9th plus 5, or x to the 9th minus 17.2, or x to the 9th plus 100, or x to the 9th minus 1. All of those would have the same derivative, which would be 9x to the 8th, because the derivative of a constant is 0. So where differentiation and antidifferentiation become very different is that when you do antidifferentiation, you have to take into account that there could have been a constant added to that function, that when you took its derivative, it became 0. So we include it by calling it C. C for constant. That C could be positive, negative, decimal, ginormous number. It could be anything. So in the end here, we would say that our antiderivative f of x would be x to the 9th plus c. And its derivative, if we wanted to double check, here we can do a check, is let's find f prime of x. Well, f prime of x to the 9th is 9x to the 8th, and the derivative of c is just 0, so that matches what we were given. So we did indeed find our function from its derivative. Let's see if we can figure out a few more antiderivatives. What function has a derivative that is e to the x? Well, hopefully, because it hasn't been that long since we did this in Chapter 4, you'll remember that that function was, in fact, just e to the x. But remember, it could have had a constant, so it's also plus c. What if we did e to the 2t? Well, if you remember, we had a rule that said the derivative of e to the kt, right? The derivative of e to the kt would have been ke to the kt. So we know, in fact, then, that this antiderivative, this function, had to have started as some form of e to the 2t. But the catch is that we don't have this k, we don't have a 2. So there must have been something there that got rid of the 2 when we multiplied it. Well, the only way I know to undo multiplying is division. So we must have had a 2 being divided. And then don't forget our c. The other way we could have written this one would be 1/2 e to the 2t plus c. What happens is that 2 wasn't there, so it had to be multiplied by something that would make it 1. Let's shift a little now from exponentials to polynomials. Let's have a look at g prime of x is equal to x cubed. So that's our derivative is x cubed. Remember that our power rule says in order to find the derivative, we would have had to bring the power down to the front and then take 1 away from the power. So the way we undo that is we have to now add 1 to the power because we're doing our power rule. So our original function g of x had to be some form of x to the fourth. Well, if we left it as just x to the fourth and we took its derivative, that would be 4x cubed. However, we have a 1x cubed, which means when we brought the 4 down, something was there to counteract it. So that would have been a 1/4, or dividing by 4, because now if we took this derivative, we would have 1/4 times 4, which gives us the 1 that we were looking for. And then the x to the fourth would go down by 1 to 3, and we would get x cubed. So that would work. And we can't forget our constant, because remember, the derivative of any constant is 0. What about if I looked at q prime of t is negative 5t? Well, we have to remember that the power of that t is 1. That is negative 5 times t to the 1. So that t to the 1 had to have come from, I hope you guessed this, a t to the 2. And we still had that negative 5 along for the ride. But what happens then is, if I left it this way, and I still had just negative 5t squared, what would have happened if I took that derivative would be I would get negative 10t. But I don't have negative 10, I have negative 5, which means that I must have to divide by 2 to take it back to the negative 5 up here. And then I could have had a constant. So there is my function. If I want to check my work, I take the derivative of my function, q prime of t. And I would get negative 5 over 2 times 2t to the 1. And the derivative of c is 0, so we just end up with negative 5t. The beautiful part of doing all of this anti-differentiation is that you can check all of your answers by taking its derivative to make sure you get back to what was given to you. Let's try something that looks fairly simple, but may not be immediately obvious. I have h prime of x. Well, h prime of x here is equal to just 3. Can you think of any function whose derivative would just be 3? Well, hopefully you said, sure. How about 3x? If you'll remember from our power rule, we had a special note on that one that said if we have a number times x, its derivative is just that number. So hopefully you remembered that, and you would say, oh, that means our original function had to be 3x. And then we can't forget our favorite, plus c. In this last one, we've got r prime of t is equal to 3 over t. So what is the only function that you can think of whose derivative would be 1 over t? Something we didn't do very long ago. I'm hoping you remembered that that would be the natural log of t. The only thing that's different when we're doing anti-differentiation and it involves logs is that we have to throw on an absolute value around what we're taking the natural log of, because you cannot take the natural log of a negative number. And without having any limitations to what t is, we can't be guaranteed that t was positive. So we have to throw on an absolute value to make sure that what we're taking the log of is always positive. And we can't forget our trusty plus c, that constant. I think after exploring some ways to find some antiderivatives, it would be helpful to have some notation to tell us that that's what we're trying to do. So what we're going to do now is we're going to define an indefinite integral. Suppose that f prime of x is a function whose antiderivatives are f of x plus c. The standard way to express this fact is to write it as the integral of f prime of x dx equals f of x plus c. That funny elongated s is called an integral. So the symbol is called the integral sign, and the entire notation, the integral of f prime of x dx, is called an indefinite integral and stands for antidifferentiation of the function f prime of x. We also, now that we understand what an integral is, can define some rules of antidifferentiation. So the first one is our power rule, which says the integral of x to the power r dx is equal to 1 over r plus 1 times x to the power of r plus 1, all plus c. So that was the same as saying our integral of x squared dx would be, well, the power r here is 2, so it's 1 over 2 plus 1, which is 3, x to the 2 plus 1, which is 3, plus c. And this is something we sort of stumbled into when we were looking at the examples earlier. You add 1 to the power and you divide by the new power. That's what our power rule of antidifferentiation is saying. Our exponential rule, which we also figured out, was if we have the integral of e to the kx dx, it is 1 over k times e to the kx plus c. So that was when we had something like the integral of e to the negative 5x dx. Well, that would be 1 over negative 5 e to the negative 5x plus c. The log rule is the one I sort of took us into head first on that last example, on example 1, which says the integral of 1 over x dx is the natural log of the absolute value of x plus c. And x just can't be 0 because the log of 0 doesn't exist. This one is important for the same reasons I mentioned in example 1, because you need to know that x is always positive because you can't take the log of a negative number. And this would be a great time to remind you that Pearson will not count it right if you forget the absolute values. So when you're doing this homework on Pearson, if you have a log, a natural log, remember that when you plug in your answer for your antiderivative on Pearson, you have to put absolute values around what you're taking the natural log of, or it won't count it right. Some of the rules that we had in place for derivatives are also in place for antiderivatives. If you remember when we took derivatives and there were multiple terms that were added or subtracted, we were able to take the derivative of each term separately and add them all together, or subtract, as the case may be. When we do antiderivatives, we can do exactly the same thing. So that's our sum rule. It says if we have the integral of f of x plus g of x dx, we can break it up into the integral of f of x dx plus the integral of g of x dx. And when we took derivatives and we had a constant in the front, we had a number times a function of x, we were able to just bring the constant along for the ride for the derivative and then multiply it by the derivative of the function. The same thing happens with antiderivatives. If you have the integral of k, which is any constant, times a function, you can move the k outside of the integral. So that is our constant multiple rule here, where you can move the k outside of your integral. And it's just along for the ride, again, just like when we did derivatives. Let's see now if we can put some of these rules into action. You might find it helpful for the next few examples to have the page that you wrote down some of these rules above where you're working on the examples. So that way you can look at your rules as you need to while we work them out, or you can pause it, go look at your rules and try to figure it out on your own, and then come back and see if you got the same solution I did. So if you want to pause it and try it on your own, you can certainly do that right now and try to find the integral of 4 over x minus x over 4 dx. If you want to go ahead and move forward with me, we can do that. And if you've tried it and want to check your answer, let's do that. So we can put into play here a number of the rules we were just given. We've got the integral of 4 over x minus x over 4. Well, our constant multiple rule and our sum rule says I can make that the integral of 4 over x dx minus the integral of x over 4 dx. That's our sum rule. But I can use that constant multiple rule to change it a little bit more by bringing this 4 to the outside and making it the integral of 1 over x dx. And for this second one, it may not be obvious what number it is you can bring out, but x over 4 is the same as 1/4 x. So in that case, you have 1/4 times x. You can bring 1/4 to the outside and leave just the x dx on the inside. Now we bring the 4 along for the ride and we figure out what is the antiderivative of 1 over x. Well, hopefully you remember that the function natural log of x has the derivative of 1 over x. So we have the natural log of x. But remember, when we take a natural log as an antiderivative, we have to put absolute values around the natural log of x. We have to put the absolute values around the x because x could have been positive or negative since we don't know for sure. And then we have 1/4 times, well, this is x to the power of 1. If we use our power rule of antidifferentiation, that means this is 1 over 1 plus 1 is 2. X to the 1 plus 1 is 2. And we'll add our c. So if we put all of our terms together, we get 4 times the natural log of the absolute value of x minus, now this is 1 over 8 x squared plus c. So here we applied the sum rule, we applied the constant multiple rule, and we did the log and the power rule. So we have our log rule and our power rule. So we put into place all of those properties and rules we've learned on the past several slides. What I'd like for you to do is I would really like for you to pause on this one and try it before you go on to see what the solution is. This one asks for the integral of x minus 2x squared plus 1 over 3x, all with respect to x. So pause here and try it on your own and then come back to see if we got the same solution. Hopefully, when you worked through this, you turn it into the integral of x dx minus the integral of 2x squared dx and plus the integral of 1 over 3x dx. Well, now we can break them up separately, but let's do some constant multiples and try to pull out some numbers, some constants to the front. The first one we're going to leave is just the integral of x dx. The second one, we can pull that 2 to the outside and now make it the integral of x squared dx. What's not obvious is What is 1 over 3x? Well, 1 over 3x, we can break into 1 over 3 times 1 over x. And if that's the case, we can pull this 1 over 3 to the outside of the integral, and we'll have 1 over x dx on the inside. And now we can apply the power rule. Well, this is an x to the 1. So when we add 1 to that power, it becomes 2. So we end up with 1 over 2 x to the 2. For the second term, we leave the 2 on the outside. Well, its power is 2. When we add 1 to that, we get 3. So 1 over 3 x to the 3. Both of those are power rules. For this last integral, we have 1 over x. We leave the 1/3 on the outside, and we find the integral of 1 over x is the natural log of, don't forget the absolute value of x, and then don't forget your c. So the only cleaning up we need to do is we can multiply 2 and 1/3 here. So our final solution here, our final integral would be 1/2 x squared minus 2/3 x cubed plus 1/3 the natural log of the absolute value of x plus c. And do not forget your plus c on Pearson, because it will yell at you and say you forgot your plus c, and it won't mark it right. So don't waste an entire attempt because you forgot your plus c. I will tell you that is the most common mistake though when integrating. Oftentimes I forget it too, and I have to go back and go, oh, I forgot the c. So I even went through some of this homework and once or twice forgot the c and had to redo the problem. So make sure that you don't forget your plus c on any of your problems. Let's try one now that has an e to the kx. We haven't had a chance to apply that rule again since we learned it. So example 4 asks us to find the integral of -8 e to the -3x dx. So we already know we can move that -8 to the outside by our constant multiple rule. And now we have -8 times the integral of e to the -3x dx. And remember, our exponential rule told us that that becomes -8 stays here. This becomes 1 over k e to the kx. Well, our k in this case is -3. So we get 1 over -3 e to the -3x, and then plus c. And the only simplification we need to do is -8 times -1/3, which gives us 8/3 e to the -3x plus c. Let's try another exponential. This time I have a constant times 2 different terms on the inside of the integral. So in this case, it's actually easier to go ahead and distribute the 2 and say that this is the integral of 2 e to the 2x plus 6 dx. So what I can do is make this 2 times the integral of e to the 2x dx plus the integral of 6 dx. Well, we already know from our exponential rule that this is 2 times, and what we have here is e to the kx, so it's 1 over k times e to the kx. And in our case, k is 2. So we have 1/2 e to the 2x. And then what happens is when we get to the 6, we have the integral of 6, which came from, hopefully you remember from example 1, 6x. So now we have 6x here plus c. Well, 2 times 1/2 is just 1. So what we really end up with in the end is e to the 2x plus 6x plus c. So sometimes we can get a problem that's going to give us a piece of information that will actually help us find out what our constant was that we keep adding to all of these problems. And that's the case with example number 6. Example number 6 wants us to find the function such that its derivative is x squared. But it also tells us that f of 3 is equal to 15. So let's start with the first part. Let's just do this part. Let's look at that. So we know that we need to find f of x. And f of x is now going to be the integral of f prime of x dx. Well, f prime of x is x squared. So f of x is the integral of x squared dx. So what we need to do is we need to employ our power rule, which says, okay, that means that f of x is equal to, well, add 1 to the power would make it 3, so it's 1 over 3 x to the third. But don't forget your plus c. So we can check off this first part. We found the function, what it could potentially be, but we don't know what c is. Well, that's where this point enters the picture. We also know that f of 3 equals 15. So we can plug in 15 for f of x, and we can plug in 3 for x, and the only thing we don't know in that case then is c. Well, 3 cubed is 27, and 27 divided by 3 is 9. And then when we subtract the 9 to the other side, we find out that c is equal to 6. So our overall solution to this problem would be 1/3 x cubed plus c, which is now 6. So 1/3 x cubed plus 6. I'd really like for you to try example 7 on your own before we go through it, because it's a very similar type of problem to 6, except that now we're doing an exponential of the form e to the kx. So pause here, try this problem, and then come back to see if you've got the same solution that I did. Well, we know that f of x is the integral of f prime of x. So we know that f of x then is equal to the integral of e to the 0.5x dx. So this is where we have to employ that exponential formula that said, oh, if it's e to the kx, its antiderivative is 1 over k, e to the kx. So that means we have our function is 1 over 0.5 e to the 0.5x and plus c. The only thing I'm going to say here is go ahead and simplify 1 over 0.5, because that number becomes 2. 2e to the 0.5x plus c. And I'm sure someone will ask me, how is 1 over 0.5 equal to 2? That's the same as saying I have 1 over 1/2, which means if we look at it in fractions, that's 1 divided by 1/2, which is 1 times 2 over 1, which is 2. So when someone wants to ask me about that later, I wanted to make sure you already had it in case you're watching this late at night and don't get a chance to ask me. So our last step on our problem is to say that we know f of 0 equals 8. So we know that f of x is 8 when x is 0. Well, that becomes e to the 0. Anything to the 0 power is 1. So this e to the 0 becomes 1. So we end up with 8 equals 2 times 1 plus c. Or, once again, 6 equals c. I promise not every problem has c equal to 6. The ones I made up just happened to both have c equal to 6, completely by chance. So let's write our final answer here. F of x is equal to 2e to the 0.5x plus 6. If you would like to do more work on this section, there are more examples in your e-textbook on Pearson, and there are more resources in the distance learning module folder for section 6.1 if you would like to look into more problems. Also, don't forget that I have office hours where you can come and visit me if you have questions.